So this next talk is about restoring reflective code loading on macOS, and we will define, articulate, describe what exactly that means. And I'm glad Luke went before me because this is a great segue into this talk and mirrors some of the concepts he talked about, including the fact that it's very difficult to detect things that are running in memory. Come on, computer. It's like, I think running Zoom and Keynote at the same time is not a good idea. Yeah, it's stuck. Oh, there we go. Okay. Hit spacebar 10 times. Okay, so I always like to start my talks with articulating what my goal for the audience is, what you will learn. And as we can see here, basically there are one main thing, and that is everything related to reflective code execution in memory, and why this is a must-have for malware, even on macOS. And you might be wondering, Patrick, why are you talking about what malware should do? Well, honestly, it's a topic that's dear and near to my heart, and we'll see that one of the takeaways is that if this is a capability that I can figure out, it's no far stretch that advanced adversaries, three-letter agencies, likely have this capability already or could have figured it out themselves. So for me, it's very important for us to have public transparent discussions about offensive capabilities and also then point, as Luke did as well, some of the shortcomings or challenges of detections. So hopefully Apple can give us the tools and insights to detect that. So we're gonna start with some background and history. We're gonna then talk about approaches on macOS 15 and 26, and then we're gonna end with detections. Well, you know who I am, so I'm gonna skip this slide. I do wanna start also talking about some resources because there's been a lot of research previously on this topic. There's a great article by Red Canary talking about reflective code loading. Back in 2015, I gave an interesting talk that also talked about some of these techniques. And then Adam Chester has done some great research as well. We'll see, though, these are all pre-macOS 15, and Apple really made some significant changes that essentially undermined all this previous research. However, this research is very foundational and something I utilized a lot, so I wanted to give it a shout out. All right, so what is reflective or in-memory code loading? We're talking about the execution of compiled code directly from disk. Basically, payloads that are never written to disk, or if they are written to disk, it's only in encrypted form. So the idea is the hacker has some access already to an infected system via an exploit, an infected Xcode project like Luke showed. And the idea is then a small loader will connect out to the internet and download a second stage or more comprehensive payload that then is directly executed from memory. This is known as reflective code loading, in-memory code execution, pick your term. But the key concept is this compiled binary is never actually on the file system. And we'll see this is problematic for detection capabilities. Now, you might already know this, but one of the reasons this isn't maybe as easy as we think it is because that compiled binaries on disk are very much different than they are in memory. Specifically, they are optimized for storage. So for example, one thing is the layout is totally different. So you can't just take a compiled binary and nmap it into memory and say go. That's just not gonna work. Not only is the structure different in memory, but there's things like dependencies. And so this is a key concept to understand up front. On disk, binary is totally different from a binary in memory. Now, why do we care about in-memory code loading in the first place? Mostly because Apple decided to prioritize privacy over security. Now, often privacy and security are aligned very well, but unfortunately, sometimes they are not. And this is an example. So Apple has made the executive decision, and I'm not saying I blame them, which is basically on macOS, no process can read the memory of another process. And at face value, this is actually seems like a very good idea, right? If malware gets on your system, it should not be able to read, for example, cookies in the browser process or authentication tokens in the login process. So that's all well and good. An unfortunate side effect, though, is if we are executing something directly from memory, no security tool can read our memory space as well, which means our payload is essentially 100% invisible. And we actually see this time and time and again where advanced adversaries actually really love Apple's commitment to privacy. Another example would just be the iPhone, right? iPhones are very, very difficult to hack, but advanced three-letter agencies, nation states, Israeli companies have zero-click vulnerabilities. And if you think about it, once that exploit fires and the payload executes in iOS, like no one's discovering that. You can't even list running processes on iOS. So again, the bar for iOS is very difficult to get into, but once you're in there, it's such a secure black box that also means that security tools have no insight what is going on. So now you used to be able to read memory in macOS via the task for PID API, but Apple has basically said this is a vulnerability. Again, they think that no process should ever be able to read the memory of another process, which generally makes sense, but this also does include security tools, again, meaning that in-memory payloads are invisible and essentially undetectable, which is great for attackers, really not ideal for users and those of us writing security detections. Now, you might be thinking, well, Patrick, isn't all code executed from memory? And yeah, technically it eventually is, but what normally happens is the user double clicks on some program that's sitting on disk, and behind the scenes, the loader, which on macOS is known as DYLD, takes that binary and performs all the actions to get it ready for in-memory code execution, normal in-memory code execution. So what normally happens, say you double click on calculator, DYLD takes the calculator binary, maps it out, changes the format, sets the memory permissions, loads the dependencies, sets up initial register values, and then, yes, jumps and starts executing. So these are some of the steps that are involved, and it's actually super, super involved. DYLD is open source, but it is thousands of lines of code. And again, this is all because an on-disk binary and an in-memory binary is totally different. But at the end of the day, the binary is copied into memory and it runs from memory. So that's an important point to make as well. So if you're a hacker, or I guess the more PC term now is red teamer, it's really important to understand that most security mechanisms and detections on macOS are based around file system. And so there's some great quotes that articulated well that basically say that, you know, the file system is very carefully examined. This includes third-party security tools. For example, when a new process starts, they go and scan the binary's on-disk image, because again, the security tool can't read the binary's in-memory image. And this includes Apple's security mechanisms, XProtect, MRT, Gatekeeper. They are all checking on-disk payloads, binaries, et cetera, et cetera. And Matt, who does a lot of forensics research, has a great quote as well. And you know, he does a lot of great research on Linux and Windows. And one of the reasons he doesn't do a lot of work on macOS is you really can't do in-memory scanning unless you have some kernel extension, which now is very difficult to get run. You have to boot into recovery mode, reduce the privileges. It's just not useful for a deployable security tool. So as a hacker, if you use in-memory payloads, they are going to be invisible and cannot be captured, which is awesome. Like, hackers are stoked. So let's look at some case studies of this. And I'm actually going to focus on a Windows case study because it's one of my favorite malware samples known as Gauss. Gauss, according to the media, is attributed to the Israelis. And one of the really interesting things about Gauss is it had an in-memory loader that would load and decrypt payloads only in memory. Gauss was discovered eventually by the AV community, I believe in 2012. They also captured the encrypted payloads. But because the encrypted payloads were environmentally encrypted, which means they were actually encrypted to only decrypt on the targets where the implant was designed to run, even to this day, we have not been able to decrypt the payloads. That is insane. That is awesome. So like the Gauss authors are like, super stoked. They're like, yeah, you captured our in-memory payloads, but since we securely encrypted them, like it's been, you know, a decade plus and they're still secure. That is incredible. And so this is Gauss. The NSA also has some interest in environmental code generation. So there's some patents that they were granted. I do want to point out that the names of patents themselves are not classified. That's all I'm going to say about that. So now back to macOS, because hopefully, again, that really illustrates the power of this capability, right? You can have in-memory payloads that are environmentally encrypted, and even if they're detected, eventually, nobody is going to be able to break that. Super cool. So if you're a macOS defender, like, we showed why this is great for hackers, but for defenders, like, good luck. Like, there's not much you can do. And this, in my opinion, is kind of a problem. We will talk about some indirect reactive methods that can at least indicate that in-memory code execution is happening, but even in that case, you're not going to be able to capture the payloads. So I really don't know what we can do. Okay, so let's now talk about some specifics. I think I've made the case why in-memory code execution is awesome, why if you're a hacker, you should be using it, and why if you're a defender, you're hoping that hackers don't use this. So let's talk about a brief history, because this is something that has actually been done for a while. It all started in 2005, where Apple actually released a code sample on the official apple.com webpage that said, this is how you do in-memory code execution on macOS. And they released this project named Memory-Based Bundle, and it is a sample that shows how to execute a Mach-O code directly from memory rather than from a file. This is awesome. This is exactly what we wanted to do. And this is great. And this worked all the way back to macOS, or I guess at the time, OS 10, 10.3. A few years later, in 2009, the very informative Mac Hacker's Handbook was released, and they included a shellcode-based payload that essentially re-implemented Apple's in-memory loading that allow you to execute compiled code directly from a shellcode-based payload. Super, super cool. Around that same time, I was dabbling in offensive macOS capabilities, and I created a utility tool, an implant that utilized the same approaches that Apple was to provide in-memory code execution. Here's some of the loader source code. We will dive into some of the specifics as well. So this was in 2009. It took till 2017 until public malware samples caught up to this fact and were like, yeah, this is a cool thing to do. So that's almost a decade. That's insane. So they were a little late to the party, but in 2017 and beyond, they joined the fray. And since then, every year we have a few samples of macOS malware that has in-memory code execution capability, for example, to execute their second stage payloads and other modules. So let's look briefly at some of those macOS malware specimens, because although they support this capability, the way they did it is incredibly lazy. So one of the first samples is Apple Juice from 2019. I was one of the first ones to analyze it, and the media was like breathless. They were like, new Mac malware from North Korea is fileless. And yeah, I guess that was kind of cool. But if you look at how the malware implements that, we can see that it has a method named load from memory. It was nice the hackers left in the method names. It made it actually pretty easy to analyze. And if we look at the memory to exec method, it calls two NS APIs. We'll dig into these more, but these are the Apple APIs that actually supported in-memory code execution. Again, and this is the mechanism that Apple's code released in 2005 used as well. If you want to read more about that, there is a blog post about that. But I was looking at that closer and I was like, you know what? I think I've seen this before. And sure enough, a few years before, Cylance, cybersecurity company that got acquired, I think, by BlackBerry, so they don't exist anymore. They did some research and they published how to do in-memory code execution. Really not that novel because Apple had also originally released code. But the interesting thing was it brought a little bit more public attention to this technique. And what the adversaries had done was just copied and pasted Cylance's code verbatim into their malware. So here's kind of a diff. You could see Cylance's code and a screen capture of the disassembly from the Lazarus Group's North Korean hacker code. And they were using the exact same code. So this is interesting. It shows that malware authors are, well, maybe lazy, but also they are paying attention to what cybersecurity companies are blogging about and posting. Another case study is from 2020, Evil Quest. And if we look at Evil Quest, it has a method named run from memory. So again, malware authors left in very descriptive method and function names. And if we look at the disassembly, we can see, again, they invoke the same NS APIs, very similar to Apple's code, to perform in-memory code execution. And actually, if we decrypt the string that they use in this loading, it matches the name that Apple used in their code, memory-based bundle. So this is also not original. They just went and grabbed Apple's sample code from 2005, recompiled it, and then got in-memory code execution. Okay, so let's now dig a little bit deeper into how one achieved in-memory code execution by looking at closer at Apple's example code and some of the other specifics. Turns out it's actually super easy. And again, thanks to Apple for releasing this sample code. Basically, 3 steps. Step 1 is you read the binary into memory. And you might be like, wait, Patrick, you said we're not reading files from disk. Yeah, that's true. You could also download it directly from memory. The point is we're just copying a binary from somewhere into memory. So this could be like an encrypted binary, for example, one of Gauss's payloads. I mean, that was Windows, but same idea. Or what we would more likely do in a real operation is download this payload into memory. At this point, though, we just have a binary in memory. It still has the binary file format that looks like a binary on disk. Nothing special at this case. So step 1 is just, very basic stuff. Nothing special, no magic. The magic comes in the next 2 steps, basically where we call ns create object file image from memory, and then ns link module. And then finally, what we do is we resolve the entry point and invoke it. So step 2 is really where the loader magic happens. When you call these 2 APIs behind the scenes, this is calling into DYLD. Again, that's Apple's dynamic loader. And it's taking your in-memory binary image and getting it ready. So it's going to remap all the sections. It's going to set the memory permissions. It's going to load the dependencies. It's going to rebase it if necessary, all the things that an operating system loader normally does in these 2 APIs. So really nice that Apple gave us these APIs. And all was well and good in the world of hackers until DYLD3. And in DYLD3, Apple was like, you know what? We actually don't think this is a good idea to have an API to execute code directly from memory. In 2005, it was a cool feature, but now it's only being used to load malware. And also we understand that security tools don't have a great time detecting this. So what we're going to do without telling anybody is essentially neuter the APIs. And so if we look at the source code for NSLink module, and this is in DYLD's open source code, we can see that there's a comment from Apple that says, hey, now if anyone calls this, you know what we're going to do first? We're not going to execute the binary directly from memory. We are going to actually write it out to a temp directory and then invoke the loader normally to load it from memory. Bummer. So if you compile now, for example, Apple's code or execute any of the malware samples that supported this in-memory code execution and execute them now, if you run a file monitor, you will see that is exactly what is happening. Behind the scenes, Apple is now writing out the in-memory image to disk and then loading it using normal loader code. So that really is a bummer because it basically means that in-memory loading is completely undid. Security tools can now monitor and scan the temporary directory, pick up the payloads when they're written to disk. Yeah, not cool. And so I tweeted about this because malware was still being released with these techniques. And I was like, yo, this doesn't work anymore. And if you're a security vendor, you should be monitoring the temp directory where these in-memory payloads are now being written out by Apple. Andrew Case, I think he works for Velexity or one of the forensics company, was like, RIP, this was a great way. And so bummer, right? Well, as is always the case, Apple's security mechanisms are often a obstacle, but really not a showstopper. So now I want to talk about in-memory code execution in macOS 15. I want to essentially restore what Apple took away from us. So the goal is to restore the ability to execute binaries directly from memory without having to write your loader from scratch. Yes, you can always write your own loader. This is what malware does on Windows, but writing a loader is incredibly difficult, a ton of work, super complicated, and just not something you want to do. And there's two observations, and that is in-memory loading is like still supported. I mean, like I said, the binary, when it gets read into memory, the loader maps it all in memory and eventually executes it from memory. It's just not now supported directly via the APIs. And then also the loader code, DYLD, actually runs in our own process space, giving us a lot of options and flexibilities. So I had a few ideas. Some of them are like mildly neat. I want to talk about them because they're mildly neat, but we will also get to a more elegant solution. So the first approach I thought about is why don't we just use a RAM disk and then still use the now neutered APIs? So a RAM disk is basically a block of memory that the operating system will treat as a file system. So if we reverse engineer Apple's NS-linked module, we can see that it's now neutered to write out any binaries in memory first to the temporary directory. And they do this by calling the get-env function on the tmp dir environment variable. Well, since this is running in our process, we can change that environment variable to anything we want. So what we can do is we can create a RAM disk, which again looks like a file system, but is actually in memory, set tmp dir to our RAM disk, and then invoke the normal APIs. They will write out the binary to what they think is the file system, but it's actually our RAM disk, which is in memory, and then load it from that RAM disk back into memory and execute it. So this is kind of neat because if we execute this, and this is the steps how to do this, you can create a RAM disk, you set temp dir to the RAM disk, and then we invoke Apple's memory-based bundle. We can see that our in-memory payload is actually written out, but now is written out, as I mentioned, to the RAM disk, which is really memory. And that's great, but the problem is a RAM disk, even though it is in memory, acts as a file system, which means two things. A, file system events are still generated. So if there's an endpoint security client, they will get a file system notification. And B, anyone can read from the RAM disk. So even though it's in memory, since it's kind of a file system, security tools could read that. So kind of one step forward, half a step forward. So I continue to keep digging, and I said, okay, going back to NS-link module, again, this is the API that Apple has now neutered. After they get the temporary directory, they hard code the file name that is used to write out the memory payload before they execute it. And it's not a full file name, it's like a format string, but it always starts with ns create object file from memory -xxxx. And security researchers notice this as well and say, hey, this is actually a really good detection mechanism, because what you can do now is basically just create a file monitor that looks for those specific files prefixed with this hard-coded file name. And if you see any of those being created, you know it's someone who was trying to do in-memory code execution. And you actually really want to collect that, because there's not a lot of legitimate software, none that I'm aware of, that uses these APIs to do anything legitimate. So security tools can and were matching on this file name. So this means even if we were using that RAM disk approach, security tools could still pick that up. And I said, okay, well, what are they doing with that file name? And it turns out they were using the strlcat API to build a full file name using that prefix. And strlcat will copy up to a specified size to make sure there's no buffer overflow. So we can exploit that by creating a very, very long file name. And since the NS object file image from memory is only used in the file name, if we have a very long directory, we can essentially overwrite, in a sense, or prevent that from being added to the file name in the first place to create a file whose name doesn't have that hard-coded value anymore that security tools are looking for. So we do that here. It's maybe not the most elegant, but our point is we are essentially overriding the hard-coded file path that everyone's looking for, allowing us to create memory bundles that aren't going to be detected if someone's looking for that NS create object file image from memory. So again, a little bit of progress. Another interesting improvement was created by Adam Chester. He does a whole bunch of neat research. And he basically said, you know what? What I can do is I can patch the loader at all the places where it was writing out the file to disk, and instead redirect it to my own code so that I can have the direct execution of binaries from memory. And he released the proof of concept, and it actually works. And it's solid. But the problem is it's very intensive in the sense that it requires you finding certain offsets, changing memory permissions to map or patch rather the loader. So it's great, and I'm not knocking it, but it's rather involved. So after reading all this and trying the RAM disk stuff, I kind of took a step back and then said, you know what, I want something that is a little simpler, and I want to restore the ability to execute binaries directly from memory without having to write my own loader, without having to patch the loader, without resorting through any of these hoops. And then I was like, kind of had this shower thought, like, can I just use an older version of DYLD? Spoiler, yes. So this is like the most important slide, but it's also like the simplest slide. So I guess it's like an elegant solution in its simplicity. So since DYLD is open source, and since older versions have the APIs that are not neutered, we can just grab DYLD's source code, compile it directly into our own loader, and then invoke it directly. And since we're using DYLD, it still does all the crazy work for us, but the APIs are not neutered because we're using an older version. So here's the code to basically do in-memory code loading on macOS 15, and it's like 18 lines of code. So I have first compiled in an older version of DYLD that hadn't been neutered by Apple. And the first thing we do is call into some of its more internal APIs. Again, these are the older ones that aren't neutered. So we load the binary, instantiate from memory. We then perform the link step by calling its image.link API. I have no idea what that's doing behind the scenes. I mean, it's linking the binary and getting it ready for code execution, but I don't have to know any of the details. It's complex DYLD code from an older version that we have compiled in. And then finally, we execute the initializations for example, the constructors. So now I wanted to test this. So what I did was I compile this into a simple loader. The loader would go out to a URL, download a precompiled binary, and load it. And this worked. I wasn't super surprised because I was like, yeah, I'm just using an old version of DYLD. But at the same time, I was like, well, that was easy. You know, it's one of those solutions that I put a lot of thought into it. And then the end solution, I was like, I probably should have thought of that earlier. But I guess it's about the journey, not the destination. And an interesting thing is, if I ran a file monitor, I confirmed that no files were created. So this also wasn't a surprise. I knew the older versions of DYLD didn't write out in-memory images. That was only in the new versions that Apple neutered. And since I was using an old version, no surprises there. But I wanted to confirm. Now, one thing about the original research I did is it didn't support Objective-C in-memory payload. So you could download and execute a C payload, a C++ payload. But as soon as you added Objective-C or Swift code to your payload, it would crash. Super annoying. And this turns out that DYLD literally knows nothing about Objective-C. Objective-C is essentially a completely different runtime, and it's Greek, it's Latin to DYLD. What DYLD does is it depends on libobc.a to do the Objective-C registration. And you know, my code was just using the old version of DYLD, wasn't taking into account any of the Objective-C specifics. And I was pondering on this, and I hadn't really tackled it. And then, like, literally 2 days ago, Ryan tweeted, and he said, you know, hey, I was thinking about Patrick's reflective code loading because I published a proof of concept a while ago. And he's like, it's great, but it doesn't support Objective-C code. And he was doing some Googling and talking to LLVMs, asking them for help. And AI pointed him to this article from 2018, which did exactly what we needed to do, which is registering in-memory Objective-C payloads. Now, they weren't doing it for nefarious purposes, as is often the case, but they were doing it for some debugging stuff. So this is really great tech note that goes into exactly how one basically can register Objective-C classes and methods that weren't originally on the file system and or dynamically created, which is essentially the same thing for us. Ryan went so far as to grab the code from this article, create a PR for my code. And if we look at the code for that, what it's then doing is actually parsing the Objective-C sections in our in-memory payload and then registering them all with the Objective-C runtime. This is what I hadn't been previously doing, which is why if we look a few slides back, Objective-C payloads would crash when we tried to execute them. So with that PR merged in, thanks to Ryan and this article from 2018, the in-memory proof of concept now supports Objective-C payloads as well. Super cool. Swift is a little trickier, but it actually still works. You just have to make sure your loader and the payload are compiled with the same version of Swift. It's because a lot of Swift versions are incompatible. This is also why I refuse to write Swift. It's changing all the time. Rude. But this is cool. So now we have Objective-C and Swift payloads that can be executed from memory. Now, the next thing I want to talk about is the hardened runtime, because the hardened runtime actually thwarts or breaks this. And this is because the hardened runtime enforces code signing checks. And what that means is and I looked at how this is implemented, it checks what you've loaded in memory matches what you have on disk to detect tampering. Well, what happens if you don't have anything on disk? The hardened runtime is like, yeah, GTFO, I don't like you. So it's not so much that it breaks, but it breaks. So that's problematic. And we can see that here, the code is loaded into memory, all the fix work. But as soon as we go to execute the code, the hardened runtime goes to like check the code signing stuff, and it can't find anything on disk. So it just kills the process, which is like probably what it should do. But that's annoying. Well, the good thing is Apple provides exceptions that if you specify in your binary, your loader, it basically turns off the hardened runtime, which is super nice. So you can add either of these two exception entitlements, com.apple security CS allow unsigned executable memory, or disable executable page protection. And so what I did was I just added these entitlements to your custom loader, my custom loader. Anybody can add their entitlements to any code. These aren't like protected or restricted entitlements. And then everything works perfectly. The next thing I wanted to try was, does this work on macOS 26? Because Apple does change a lot of security things when they introduce a new version of macOS. And the great thing is it works perfectly with no changes, which goes back to the fact that we are simply using Apple's old code. So again, this is a really, really good approach. Anytime you can leverage or utilize Apple capabilities, Apple technology, Apple code, it's usually going to have a longer shelf life than perhaps you writing your own loader. So this is really great, and I'm excited to mention it now. I'm hoping Apple doesn't pay attention and like break this. I know there's some Apple employees in the audience, so please don't break this because I want this to keep working on macOS 26. So if you're a hacker, this is what you should do, or a malware author. You should create a very simple loader that contains the older version of DYLD, and I've released the proof of concept, so you can just use that. You can enable the hardened runtime with the exception entitlements and submit it for notarization. Apple only prevents notarization of known malware. So if you're just submitting a simple loader, there's nothing inherently wrong with it, and Apple is not going to block that. They're going to notarize that because your loader is just loading code. Like, that's fine. That's not malicious. And again, since Apple does not allow any process to read the memory of other processes, any payloads you download and execute from memory, which now we've restored that capability, are invisible. And your loader code, if it's ever captured, reveals nothing. It just shows it's going out to a website and downloads something. Like, that gives malware analysts no insight. Like, what are you downloading? What are the payloads? Do they have exploits in them? Who knows? We don't know. I do want to point also, if you don't want to get your payload notarized, perhaps you have an exploit and you're distributing it directly to end users, that's cool. Just don't enable the hardened runtime, and then you don't need any of those exception entitlements anyways. However, if you do want to get your loader notarized, you do have to use the hardened runtime, which then means you have to use the exception entitlements. All right, so we've empowered the offensive-minded adversaries. And whenever I do that, I like to also talk about defense because the world should be balanced, right? So let's end by talking about some detections. So the first thing I said is, cool, I have this capability. I can directly execute binaries from memory using Apple's old code. Now I want to put on my defender hat and figure out how to detect that. I always start with two things: log messages and endpoint security messages, because these are usually the best two sources of events that we can ingest into security tools to detect malicious behavior. So the first thing I did, I instrumented my loader so that it would pause, and only when I hit enter, it would then trigger the in-memory code loading and execution. And that allowed me to then start a file monitor, an endpoint security monitor, and see if any events were detected. In this case, I used Brandon's Mac monitor, which he's going to be talking about at OBTS V8, which I'm excited about as well. And it basically can capture any and all endpoint security messages. I ran that while also streaming the unified log, and nothing. Not a single log message or an endpoint security event. Yee, that sucks for defenders. And I said, okay, well, I maybe have to think a little bit more creatively. And so even though security tools can't read the memory of other processes, there are some command line tools that Apple has given special entitlements and privileges to that we as third-party security vendors will never get, but Apple can give to their tools. And one of those tools is VMMap. And VMMap can show you memory mappings. It doesn't show you the contents of the memory, but it can show you what is mapped. So I ran VMMap against my custom loader that had downloaded and executed a memory payload directly from memory. And we can see that VMMap sees a memory mapping that is not backed by anything on disk. And when it sees that, it just names it dilib. And we can confirm that that is indeed our memory mapped binary because the load address is map. So VMMap, which again has a special entitlement, so it can map or tell you the mappings of other memories, can show you some artifacts that something is loaded. However, it's a snapshot. So if by the time you run VMMap, I have executed my in-memory payload and it's been unloaded, like you're not going to see anything. Also, VMMap is like a command line tool, so you'd have to find a way to like ingest its output into your security tool. Not really, I mean, it's doable, but it's not ideal. Next, I thought, okay, what about using a sample to look for running threads? Sample also has special Apple entitlements, so it can glean information about remote processes that third-party security tools cannot. It doesn't, again, give you like a full memory reading, but it can show you currently running threads. So if we run sample against the custom loader, if the in-memory payload is doing anything and has spawned any threads, which it likely will, in the stack backtrace, there will be something that sample identifies as unknown binary. It basically says, okay, I see something in the call stack, but it doesn't map to anything on disk. I don't know much about it, but I can at least tell you it's there. And I thought, okay, maybe I can flag those exception entitlements, the two I mentioned, that if you're using the hardened runtime, you have to add, because those can't be that common, right? So I wrote a little script, well, ChatGPT wrote a little script that enumerated everything in my applications directory on my box and told me all the applications that had these entitlements. I wasn't expecting to find any. 60 plus apps had that. So I was like, all right, that's a bad idea. Like, you can't flag a binary for having those entitlements as being strange because apparently everyone has them. So really the best and only solution is actually to ignore the in-memory loading component and specifically focus on what it does. For example, imagine I write a stealer and I convert it to an in-memory bundle, and I have a little loader that Apple has perhaps notarized. There's no way to detect the download and execution of that in-memory payload or to capture it. But as soon as it goes and like dumps the keychain or perhaps exfil something, those are all observable events. So what we really have to do is kind of, unfortunately, fall back to our existing behavior-based detections And if that in-memory payload does anything anomalous, flag on that. The problem is all we're going to be able to do is then flag the process, which is the loader. And the loader isn't doing anything special. It's literally just old DYLD source code. You're not going to get the payload because you can't read anything from memory. So yeah, that sucks. So conclusions and takeaways. Two main ones. In-memory reflective loading on macOS is, thankfully, still alive and well. And this is all thanks to just using an old version of DYLD. So if you're a hacker, like, use in-memory payloads. Don't be lazy. Don't write your stuff out to the file system. That's absurd. You're going to get flagged. You're going to get collected. You're going to get detected. Lame. And if you're defenders, like, I wish I had better news, but like, good luck. Because of Apple's decision, or really their failure to strike an adequate balance between security and privacy, often, as is shown here, this ultimately empowers advanced adversaries while largely crippling defenders. Now, I'll also be the first to admit, like, this is a hard problem to solve. I think it's great that Apple places so much value on privacy. I'm an Apple fanboy, and one of the reasons is because I know data on my iPhone and my Mac is not being sucked up for advertising, and it's generally secure. But unfortunately, I think Apple sometimes takes that a little bit too far. And as I mentioned, there are times when security and privacy are at opposite ends of the spectrum. And by going to all the way to one end of that spectrum and selecting essentially just privacy can have real problematic effects that, again, advanced adversary are able to exploit. Now, one solution to this all is maybe Apple could give us an entitlement to scan memory. Something I've suggested. This would have obviously some privacy implications. I don't think this is something Apple is going to do. I think what Apple will do eventually is say that code has to be code signed fully, no exception entitlements, which means you have to have an on-disk binary. But if they did that, that would break a lot of legitimate applications as well. So I think for the next few years, we are pretty much all set in terms of using in-memory code execution. So that's a wrap. I briefly want to end by thanking the friends of Objective-C. These are the amazing companies who support the foundation, my research, and all the good things. So if you know anybody that works at any of these companies, give them an American high five. I've been high-fiving people, and like in Europe, everyone's like, that's an American thing to do. So now I say, it's an American high five. So give them an American high five or hug or whatever, and thank them. And then here are the references and resources to that, because as I mentioned, this research is built on a lot of amazing previous research. And I always think it's super important to give those researchers a lot of kudos, because honestly, without them, I would not be able to continue onwards. So that is a wrap. I also posted a blog post about this. So if you go to the Objective-C blog, there's also a link then to the proof of concept, so you can download that, play with that. And as of 2 days ago, it supports now Objective-C and Swift payloads. So that's really, really cool.